everybody who is watching this video. My name is Olenjolai from beautiful country called Tanzania, and this is our national flag. I would like to take this moment to welcome you into our Tanzania online advanced secondary schools in square bracket OLENJOLAIM. In this high level or advanced schools, we have a vision that we want to incubate some students who are ready to take the classroom instructions, including the classroom instructions that we are going to give them in these programs and the ones that they used to get in the physical schools, combine them together and solve the real life problems. For example, that now we are teaching from the perspective of the chemistry. So you as the students, you have a responsibility to think, where am I going to apply these informations and what problems am I going to solve in real life? Because you went to school not to have certificate, you went to school to have a knowledge in order to solve real life problems. Okay, so you have 7 departments: departments of advanced mathematics, departments of advanced chemistry, departments of advanced physics. And we are teaching 2 classes, Form 5 and Form 6. So in total we are teaching 8 subjects, which actually should be, there should be always that we should find more than 8 teachers who are teaching those 8 subjects. Okay, but by the grace of God, I will make it myself. Okay, so we have the subject. Today we are in departments of advanced chemistry, and then we have the subject of advanced chemistry, and we want to learn the main topic is called organic chemistry. For the Form 5 or class, it's advanced organic chemistry, Form 5 and Form 5 or class 13. So this is session 3, okay? So it means that session 1 and 2 has already been taught. Where can you get session 1 and 2? Well, the answer is you have to visit our YouTube channels that's called Tanzania Online A-Level Safety School in square bracket OLENJOLAIM, so that you may get all of the previous videos before you watch this one, because this is the continuation of what we have already begun. Also, in case that you whether now at the beginnings or in the middle of the lecture or maybe at the end of the sessions, you feel from that that you want to offer the Thanksgiving offering, then you may send your Thanksgiving offering. So this number is 0759745331, so that your Thanksgiving will be used effectively to pay the running cost for this program. So if that's the case, I would like now to take you into the business that has brought us here, and the business that I want to go and discuss with you is the business of advanced chemistry. You should have some books beside you when you'll be learning this stuff. For instance, this is the syllabus for advanced chemistry. Okay, it's called the chemistry syllabus for advanced secondary education from 5 to Form 6. You should have it beside you. And also you should have at least 1 or 2 reference books. This is called the textbook. For example, this is the S-Chand. For organic chemistry, you find in S-Chand class 12. Right, class 12, or County Chand 2. Or you can have also another book, for example, Ramsden's. So you have a level chemistry. Okay, again, you should have also at least, because for organic, it's contributing questions in paper 1, and advanced chemistry paper 1 and advanced chemistry paper 2. So you should have also should have at least a review book or past papers, which actually are going to test your understanding of the particular concept, right? So you should have all of this stuff beside you when you'll be learning, and you'll be testing what I'll be telling you. Okay, so if that's the case, let us go to the business that make us to meet. I would like to do the quick review. Of lecture 2. In lecture 2, first of all, we defined or we explained to you about a terminology we call the chemical reactive. So we began on introducing to you the condition necessary for organic compounds to be chemical reactive. Okay? There are some conditions for the chemical reactive element. And then we say that we talked about types of organic reagent, types of organic reagents or reactants. And we say that we have 3 reagents. We have 3 types of reagents. Okay, so the first one we say that it is nucleophile, which we discussed in lecture 2 in detail. Nucleophile. We say that this is made by the 2 words. Nucleo means nucleus, phile means love. And then we say that the second type is electrophile, which is deficiency, which is rich in protons or positive charge, but weak or does not contain enough number of electrons. So we just introduced here, we just mentioned that we didn't even explain about what electrophile and the free radical. And then we left the homework for you. Don't know if you did it or not. That was, let's say, homework 2. So we did a lot of things. So in case that you want to get all the details, make sure that you go and you sign in by using our email, and make sure that you subscribe so that you'll be receiving notification once that we upload a new video. So, if that's the case, today we'd like to take you onto the 2 remaining organic reagents. So, let us finish the subtopic of yesterday, types of organic reactants, types of organic reactants or reagents. We said there are 3 types of reactants, and then we say we have nucleophile, electrophile, and the free radical. So then let us start on learning what is electrophile. Say electrophile. What is electrophile? You can write just the C symbol in case that is positive. So the fundamental question that you have, what is electrophile? What is electrophile? Okay? So you say that electrophile first of all, the word electrophile comes from 2 words that are electro means what? Electrons. And then phile, as we said yesterday in the previous session, phile, this is electron lava or lava. So phile means that lava. So if that's the case, where do you find electrons? In the atom, the electrons always are found in shell, right? So if you have maybe like this, so electrons are always found in the shell, while protons are found in the nucleus. So this is a species, a chemical species, which love so much to receive electrons from electromagnetic love, right? Okay. So by definition, say that electrophile so we said that electrophile, this is one of the definition. Electrophile is a chemical species. The chemical species. The chemical species which can accept, which can accept electrons from electrons donor. This electron sorting. So electrophile, that's the love sorting, or say that the word electrophile indicates that it is electron lover. Okay? We have some examples of electrophile. You can find also some other definition just that you get time. So you say that the examples, I will tell you why. Bromine but its positive sign. I'll tell you that where do they get that positive sign. Then we have fluorine but positive size. And then we have iodine but also positive. So those are the simple examples of 40. Remember I told you that the issue of nucleophile is the one that taking control of 40 of inorganic reactions because it is always formed. Okay, so if that's the case now, let me teach you about types of 40. Types of electrophile. Okay, types of 40 electrophiles. There are only two types of electrophile. Only two types of electrophile that are so the first type, we call it the positive charged ions. So positive charged ions. Positive charged ions. Positive charged ions or cations. Say negatively or positively charged ions. So say that these are this electrophile, okay, this electrophile contains an orbital which can accommodate more electrons. Okay? So, which can accommodate. Accommodation is have a way. Is it like this? Accommodate more electrons. Okay? Accommodate more electrons. So examples of these positive charged ions is fluorine, bromine, iodine. I'll show you soon that why are they positive ions. But again, we have hydrogen. Say hydrogen. So you have hydrogen. So you have hydrogen ion. I'll show you some of this bonding. We have also carbonium ion. So these are the examples. Carbonium ion, and this carbonium ion, like this. It's a functional group. It is hydrocarbon, then carbon, hydrogen, hydrogen. And here it is partially positive. We'll show you how we formulate. But we have also halonium. Halonium means that halogen. Halonium. So it means that halogens. These halogens use the symbol of X or notation of X. We have also, as we mentioned, we have chloromium, bromium, iodium, etc. So let me explain that how do we get these positive ions, because they've been shocked to see chlorine that today it has a positive ion. Why? Because you know always chlorine, if it ionizes, it's always gaining electron. Right? How comes that today it has lost electron? Okay, so let me just explain to you. Let us take chlorine as a famous element. Right? So how many electrons does it contain? 17. Right? Eh? Isn't it 17? Yes, it's 17. And then you say that if you write electronic configuration, electronic configurations of chlorine, this is equal to what? 1, so we say that simply, we say that neon remain how many electrons? I would say 7, right? So neon 7. Next it is 2, S.
3s.
Okay, 3s. Okay?
Yes.
Array S square. And then such array P. So P contains 6 electrons, if I'm not mistaken. 6 or 5. 5. Okay? So this is the chlorine atom. Chlorine atom. So then if you write that this, and you use the orbital method, so you find that you have 3s squared, 3p power 5. So you say that if that's the case, for this one, this orbital is paired. Okay? And then so then we have 5 electrons. First electron, second electron, third electron. How many remain? 2. Right? So we say that always this one, or the chlorine, needs 1 electron to reach this octet state. Right? So when it gains 1 electron, this PZ orbital will be filled. Right? But what happens under this null of forming chromium ion? So during the formation of chromium ion, if you write electron configuration, what happens? Mean that this is in case chlorine has lost the 1 unpaired electrons, right? So when it has lost the 1 unpaired electrons, we say that, okay, fine. Okay, so it's now, and then 3s, 3p. Okay, so enter the case now. What is the orbital method? So then here we have the p orbital. Okay, so then we have 1 electron. Then we don't have any electrons anymore. Here you have 1 electron, here you have 1 electron. Right? Okay, so this is the electron configurations of chromium ion. So you see that it contains such an empty orbital. So if it contains an empty orbital, this empty orbital can accommodate a new new electrons. Okay, so when you write that chlorine with positive sign, the total number of electrons is not equal to what? It's not equal to their atomic structure, right? So here it means that it contains only 16 electrons. While here to contain how many? 17 electrons. Okay? Are we together? Okay. Okay. So how do we prepare these chlorine positive ions? We call it chloronium. Listen, for example, chlorine exists in molecular structure. Fluorine also exists in molecular structure. Bromine possibly also exists in molecular structure. I want to take these other examples, right? So what happens? So in chlorine molecules mean that there's a covalent bond between one chlorine atom and another chlorine atom, right? Yeah. So what happens? Sometimes, if under certain conditions, if the bond breaks, each electrons will leave each atom will leave its electrons shared. Because here, this chlorine atom shared 1 electrons, and this one shared 1 electron to reach the octet state, which is the compound state, is the state for forming the compound, right? Are we together? Okay, so what happens? Sometimes it might happen under some condition that you find. Maybe this chlorine withdraw all electrons. And this one, because it's lost its electrons, become partially positive. So after bond breaking, so it means that when the bond breaking, you have now partial positive, and this one is the one that we call it positive chlorine ion. Are we together? That's such kind of the tendency. Again, we say that we have carbonium ion. Okay, carbonium ion. This is the hydrogen group. This is carbon. Before, this carbon has been surrounded by 3 hydrogen. Listen careful. When the bond is breaking, remember that these are the sigma bonds. So even if that you want to break them, so you need energy, sometimes you have to hit the system. So it's a sigma bond. And they left my homework about sigma bond and pi bond, but you haven't submitted. Even the comment sections. If you say that, sir, you don't read, go and write in the comment section. Okay. So for this scenario, we say that, okay, well, for this scenario, between carbon and hydrogen, which is more electronegative?
Carbon.
Carbon. Are you sure?
Yes.
Are you sure?
Yes.
Okay. So carbon is more electronegative more than what? Hydrogen. So now if this bond break, the more electronegative atom will store all the electrons. Right? And then this one will become partially positive. Okay? Partially positive. So carbonium ions, we have this kind and this guy. Dense is partially negative, but plus what? Hydrogen, partially positive. Right? So these carbonium ions now, it's the one that you are writing like this. Are we together? Okay. So now you have understood about positive charged ions as what? Electrophile. The second type of electrophile, we call them Lewis acid. Lewis acid. I gave you the homework yesterday.
Yes.
And learn about Lewis acid. So number 2, we have what? Lewis acids. Lewis what? Acids. Say Lewis acid.
Lewis acid.
Lewis acid. So who can define what is Lewis acids? Because we learned this in general chemistry. What's Lewis acid? Speak it.
Lewis acid is a chemical species which contains an empty orbital that can accommodate a pair which is capable of accepting an electron pair from Lewis base.
From Lewis base. So Lewis acid, so let us remind ourselves. So say Lewis acid is what?
Is a chemical species
The chemical species.
that contains an empty orbital.
The chemical species, or is a chemical substance. Or substance that contains what?
An empty orbital.
Pardon?
An empty orbital.
Contain an empty orbital.
Yes. Which is capable.
Which is capable. Capable to accept it. Lone pair.
Electron pair.
Right?
Yes, from Lewis.
Okay, so from what? From Lewis base. Because this. From Lewis what?
Base.
Base. So it's a student now to go and look the definition, brief description of what? Okay, so this is the proper definition. We say that Lewis acid are the types of electrophile. It means that they love electrons. All of them have 40 electrons. But when it is half electrons, we say that why do they have electrons? Because they have the space to accommodate. Right? Okay, fine. So we say, what are the examples of Lewis acid? Examples of Lewis acid. Mention at least 10. Examples of Lewis acid are, the first example is what?
Boron trifluoride.
Boron trifluoride. The other one is aluminium. Aluminium what? So we said aluminium trichloride, because you have aluminium chloride, you have aluminium trichloride, you have aluminium pentachloride. So here we say that we have aluminium, and then we have another atom that has been is chlorine. Okay, it's chlorine. Then iron bromide. As the compounds or next based is iron bromide, iron serine bromide, iron 3 bromide. Okay, so those are the examples of Lewis acid. So themselves, they lack electrons, but they contain sodium orbital. So let us verify, because according to Lewis acid, the definition say the chemical substance that contain an empty orbital. So we want first to show you where the empty orbital, right? And then see, it has a capacity or is capable to accept lone pairs, and then we see whether it's possible, it's not possible, not possible. So we say that here we have, let's say, boron. In electronic configurations, it means that boron is number 5. So boron, so we say that for that case, you say that the electronic configurations of boron, this is equal to it. Right?
Yes.
And then you say that you have what?
2s, yeah.
2s squared. Then to what?
2p1.
3 power 1. Right?
Yes.
So if you draw the orbital structure of 2s, there's no problem. So it is 2s, 2s, full with electrons. Okay. So then we say that in pH you have only one electron. Okay? Yeah?
Yes.
Okay, so it is one electron. So how many empty orbitals does it contain? 2. Right?
Yes.
Which is purity, Py and what?
PZ.
PZ. Can this accommodate? Can they accommodate? Can they accommodate electrons?
Yes.
Why? Because they are empty, right?
Yeah.
Okay, fine. So then we want to show you which tendency?
The tendency of acceptance.
The tendency of acceptance. This contains what? Empty orbital 1, 2. This is 40 for chlorine. Right?
Yeah.
Okay. So if that's the case now, it is the case because this is 2p. In this state, you find, for instance, how did he form boron trifluoride, right?
Yes.
So the way boron trifluoride we say that first of all, we promote one of electrons to come to purity, py, right? So then we say that in 2s, we have what, 1 electron, right? Are we together? Okay, 1 electron. And then we say that the p orbital okay, the p orbital, we say that now it contains 3 electrons. Okay? Are we together?
Yes.
So this is purity, px, py, pz. Okay? So when we have bromine, so we say that, for instance, if we bring the fluorine, be here, okay? So we say that this fluorine, and also here, there is fluorine which should be accommodating, right? So to draw, it means to find that fluorine is accommodating. So here we have 1 electrons, which is what, 2s, and then here again. Okay? So then suppose that this is the first thing, second and third. Okay? So for this case, this contains some periodic electrons. Right? So if that's the case, when it reacts with fluorine, it is say fluorine. Okay? So fluorine, and again here, we have fluorine atom. That's why that we have bromium, trifluoride. So where the empty orbital? This one. Empty orbital. Okay?
Yes.
So this is what makes this guy to be laser. Are you together?
Yes.
Yeah, so I'm trying my level best to illustrate everything. Okay, so then now we have showed you about uric acid and their structure. Okay?
Yes.
So similar to aluminium. So for your homework, go and draw for all of this stuff. This is 3-chlorine, excuse me. So do this homework in detail compared to what I've done in this. Right?
Yeah.
Okay, so if that's the case, we say that it is the end of 40 of electrophile. Right? It's the end of electrophile. So because we want to wipe up this section, it's better if we finish with free radical. The good thing is free radical is not longer. Say free radical. All of these are different sources that you can count and later. Free radical. Say free radical. Free radical. Okay? What is free radical? What is free radical? What is free radical? So you say that free radical we say that the chemical substance free radical is a chemical substance free radical is a chemical substance which contain only paired unpaired which contain at least not only which contain unpaired electrons in the valence shell. Okay? So we say that by definition, free radical is a chemical substance or chemical species which contain unpaired electrons. Okay? In the valence shell. Okay? That's the meaning of free radical. It's an atom or group of atoms that contains one unpaired electrons. Okay? So then we have types of what? So let us show that in a compound, how do you formulate or do you find that ampere? For instance, that's right, the electronic configurations of chlorine. Right? So if you write the electronic configuration, we have what? Neon, series. Right? Yeah?
Yes.
Series what?
Square.
Square. Then series what? Yeah?
Repeat.
Repeat. P
Five.
power?
5.
5. Uh-huh. So if you draw, you see orbital, okay, and then for series P, okay, so here we have electrons. 1, 2, 3, 4, 5. No. Only 5 electrons in P. Right? No. This electrons in there. So you see, this one, the last orbital contains an unpaired electrons. Unpaired electron. Okay?
Yeah.
Unpaired electrons. So because of these unpaired electrons, make chlorine to become free radical. So you can do similarly for fluorine. Okay?
Yes.
So examples of free radical. So examples of free radical are itself. Okay? Excuse me. Chlorine, this is the symbol. And then bromine, this is the symbol for the free radical. Then you have iodine, this is the symbol. Then you have what? Hydrogen, this is the symbol. Also, you can have benzene. CH3. So suppose that this is carbon, this is hydrogen bond, hydrogen bond, hydrogen bond, but one bond. So say that the dot represents what? Representing free radical. Okay? So you say that the dot represents what? Free radical. Free radical are unstable and they don't exist by the air ions as they do not attain stable electronic structure of the noble gases. Okay, so those are the examples of what? Examples of free radicals. So free radicals are unstable, don't exist by the air ions, so they don't attain the electronic structure of the noble gas. Okay, so I think that the main points are what I've mentioned here. Those are the examples. So once you see something that is written, this is free radical. Once you see, for example, that in case, once you see, let's say that you've seen hydrogen and then dot, this is something else, right? So this is free radical, this is free radical. This means that it's what electron deficiency, also it's also electromotive deficiency, right? So in case of free radical, you don't have too much storage, or you don't have too much details that to dig in. Just have to know the notation and then etc. etc. So from now, if you are homework, go and think now, is it possible for the nucleophile to react with nucleophile? Okay? Okay. So he said that we have this Porini. My intention is go and think about this. What do we get? If you take nucleophile, so this is negative, negative, positive, positive charge. What will you get? Again, go and think about what if you take free radical as electrophile. What do you get? Just think about that. So this is simple homework. Homework 2. Okay, so this is the end of the entire lecture of types of organic reagents, organic reactants. I thank God who have been with me. I thank you also who have taken your time and taking these sessions with me. And I would like pray to God to bless you abundantly, step to step. And I invite you into our lecture or session 3 of session 4 of the general introductions of organic chemistry. So stay tuned and stay connected, and see you in the next session.